Hello, I'm Ed Hughes, the Product Manager for SAS OR and SAS Optimization. Our focus in this video is the use of the OptModel procedure in SAS Optimization 8.1 on the SAS Viya platform. At the heart of the SAS Viya architecture is the Cloud Analytics Services Server, or CAS server. The CAS server is specifically designed to analyze very large data sets, and it also supports parallel computation, both threaded computation on a single node and distributed computation on multiple server nodes. This enables statistical and machine learning algorithms to scale to massive amounts of data. However, it's important to point out that typical optimization problems have comparatively small data, and yet involve highly memory and CPU-intensive computations. An optimization problem can take a long time to solve despite its small input data. For this reason, SAS Optimization on Viya implements more of a big computing paradigm than a big data paradigm. A corollary is that data can be moved or replicated as needed to gain additional computing capability, because moving and replicating comparatively small data isn't expensive. Another aspect specific to optimization is that the magnitude of performance improvements in optimization algorithms from using distributed processing can vary on a case-by-case basis. There are even situations where using more nodes can increase computation time, and thus it's important to be able to specify a number of nodes that's appropriate for the specific situation. We'll see how PROC OPTMODEL in SAS Optimization 8.1 supports this capability. First, a quick review of the structure of a typical PROC OPTMODEL program. This is a simple example of a knapsack problem in which you're given a knapsack, or any container, with a weight capacity and a set of items with corresponding weights and values. The optimization problem is to find a subset of items that maximizes the total value of the items chosen and satisfies the overall weight restriction. This section of the program describes the algebraic model for the problem, using a binary integer programming formulation based on the optimization-specific syntax and structures that PROC OPTMODEL provides. Next, we attach a set of data elements, which can come from any library accessible to SAS. This creates a single optimization problem instance. The third step is to call the appropriate optimization solver via the solve statement. When PROC OPTMODEL encounters a solve statement, it builds a representation of the problem instance and runs the appropriate solver. Here we use the mixed integer linear programming solver, abbreviated as the MILP solver. Initially, we solve the problem once with a capacity value of 40. We create this problem instance and execute the solver on the SAS server. These three high-level steps, algebraic model description, attaching a data instance, and invoking a solver, occur for any optimization model that you build and solve in PROC OPTMODEL. To keep things brief, we omit the additional step of writing out the details of the optimization solution. You can also use the programming features of PROC OPTMODEL. The next section of this program illustrates using the concurrent for or co-for loop, which enables you to solve a set of independent optimization scenarios in parallel. In this example, we're solving 10 problem instances with a capacity ranging between 30 and 48. This helps us investigate how changes in capacity affect the optimal solution. On a single server, the co-for loop would use threads to implement this parallel approach. Next, we'll use this example to show how easily you can modify a PROC OPTMODEL program in SAS OR to run in SAS Optimization on Viya. Let's assume that a CAS server has been started, and you have access to a CAS session called SAS CAS1 on that server. This CAS server instance and CAS session might be running on hardware that is distinct from the SAS server where your SAS code gets executed. It might even be running in the cloud. In SAS Optimization on Viya, PROC OPTMODEL has a new option called sesref equals, shown here in the first line of the program, which allows you to specify a CAS session with which you want PROC OPTMODEL to interact. Elsewhere in the program, the algebraic model declaration and associating data with the algebraic model formulation stay exactly as they were before. In SAS Optimization, PROC OPTMODEL allows access to data from any type of library that is accessible from the SAS server. The data could be in CAS tables, provided they are accessible from the session SAS CAS1. Any dataset or table referred to in any read data statement is copied to the SAS server, and remember, this is not a big cost because of the small data sizes. PROC OPTMODEL builds the problem instance on the SAS side using these data whenever it executes a solve statement. Because we specified the CAS session by using the sesref equals option, PROC OPTMODEL ports the problem instance over to the CAS server, and the MILP solver runs in the CAS session SAS CAS1 to solve the problem instance. In this case, the threaded single machine solver is invoked on a server node that is chosen randomly from the nodes assigned to the session SAS-CAS1. The solution is brought back to the SAS server for further processing. Note that the user experience is almost exactly the same as in SAS OR. The only change is that the solver executes on the CAS server. The user sets the option sesref equals to the name of the CAS session. PROC OPTMODEL manages everything else in a way that is invisible to the user. In SAS optimization, the COFOR loop in PROC OPTMODEL uses distributed processing on the CAS server. The independent runs of the MILP solver algorithm that correspond to the COFOR loop iterations are distributed among the available server nodes associated with the CAS session SAS-CAS1. Each of the 10 solver calls is solved on a single server node in the default threaded mode, so each solver call is using local parallelism as well. PROC OPTMODEL waits for all computations to be completed, collects all the results, and then executes any statements that follow the COFOR loop. The decrease in computation time depends on the number of server nodes available and on how well balanced the distributed solver-related computations are. In this example, we have a COFOR loop that has 10 iterations. Suppose the session has 10 nodes, and the model building time is minimal compared with the solver runtimes. Assume the problem instance for each iteration needs 20 minutes to solve. In this case, each MILP solver call will likely be solved on a separate node, meaning that just 20 minutes will be required overall. The speedup factor due to this distributed COFOR loop is close to 10, compared to a sequential for loop, which would take around 200 minutes. At the other extreme, assume one instance needs 20 minutes to solve, and the remaining 9 instances need just 1 minute each. Again, 20 minutes are needed overall, but here the speedup factor will be close to just 1.5 compared to a sequential for loop, which would take around 29 minutes. Even though the COFOR loop executes an obviously parallel computation task, the computational gains from using distributed computing can vary greatly depending on the details. In this example, we use the default threaded MILP solver, but this is just one of the solvers accessible from PROC OPTMODEL. This is the complete list. The superscript D indicates support for execution in distributed mode. In all other cases, the solver runs on one server node, and a superscript T indicates that the solver runs in threaded mode. It's important to remember that this family of solvers for PROC OPTMODEL and SAS optimization includes those available with PROC OPTMODEL in SAS OR and the solvers available with PROC OPTMODEL in SAS high performance optimization. Additional distributed algorithms are available only on the SAS Viya platform. Two prominent examples are a new concurrent MILP solver and a new distributed shortest path algorithm for multiple source and sink pairs. Shortest path is one of the 11 network optimization algorithms. Because the gains from distributing optimization-related computing across server nodes can vary from case to case, it's important to be able to choose a number of nodes that's well suited for a particular computation. This is especially useful with PROC OPTMODEL because it's normal for a single program to contain several calls to different solvers. This example shows how you enable this flexibility in PROC OPTMODEL. Most of the PROC OPTMODEL code is the same as before, except that for the first solve, we invoke the concurrent MILP solver, which has a distributed implementation. If we assume the current CAS session SAS-CAS1 has 10 server nodes, then execution of this algorithm is distributed over those 10 nodes. Now assume the next COFOR loop needs to run through 100 iterations, and the MILP solver is invoked once in each iteration. We've created another CAS session, SAS-CAS100, which runs on 100 nodes. You can submit a statement within the same PROC OPTMODEL call to reset the current CAS session to SAS-CAS100. This means any further solves will be submitted to this new CAS session. Thus, the 100 COFOR loop solves are submitted to the 100 server nodes. You can change the current CAS session as many times as you need, using similar resets of the sesref equals option. As you use PROC OPTMODEL in SAS optimization, you'll see there is minimal change in syntax from SAS OR. In SAS optimization, PROC OPTMODEL accepts both SAS datasets and CAS tables as input. It builds problem instances on the SAS side, but the optimization solvers execute in a CAS session, which you specify using a PROC OPTMODEL option sesref equals. You can access multiple CAS sessions from a single PROC OPTMODEL call by resetting this option. This is an important feature, given the varying benefits of distributed computation as a function of the number of nodes. This has been a brief look at using PROC OPTMODEL and SAS Optimization 8.1 on the SAS Viya platform. I hope you found this video instructive, and thanks for watching.